Welcome back, everybody. So today we're going to be talking about the quantum Fourier transform. The quantum Fourier transform, it's one of the most important algorithmic primitives that we have in quantum computing and is the heart of many of the speedups that we end up seeing, including speedups for of the Shor's algorithm, quantum gradient descent, as well as a number of other applications. So before I begin with all of this, let me start by sharing my screen and then jump in to the background, to a little bit of review on the discrete Fourier transform. So basically the discrete Fourier transform, what it is it is a linear transformation mapping C2 to the n through C2 to the n. Now, because it's a linear transformation, as we ended up seeing earlier, every linear transformation can always be expressed as a matrix. And in particular, the matrix for the discrete Fourier transform actually ends up taking a very particular form, expressed using the simplified notation where omega is equal to e to the 2 pi I divided by 2 to the n. This is what's known as a 2 to the nth root of unity, in other words. Then the Dft matrix is defined to be equal to 1 over root 2 to the n, 1, 1, 1, 1, going all the way down to 1 at the bottom, 1. And then the pattern from here goes as follows. The elements in the first row go like omega to the 1, omega 2, omega 3, all the way down to omega 2 to the n minus 1. Okay. Then the next one starts off at omega 2, then omega 2 squared, omega 2 cubed, or sorry, not omega 2 squared. It goes like omega 2, then omega 4, then omega 6, all the way down to omega 2 to the 2n minus 1. And then the next one, of course, is omega cubed, omega to the 6th, omega to the 9th, all the way down to omega 3 to the 2n minus 1. Now, the last column is very similar. And it'll continue to omega 2 to the n minus 1 squared. Okay, cool. So this is the discrete Fourier transform matrix, and it's got a number of nice properties. From the perspective of quantum computing, the most important property from Dft is that Dft here, so these are some properties. Dft is unitary. So how do we end up showing this? Well, easiest way of doing it is we'll just get the matrix and multiply it by its adjoint. So if we have that Dft dagger is equal to identity, then we know it's unitary. So I'm going to use a notation where I'm just going to be referring to the different columns that we end up having in the matrix. This is going to be column 1, column 2, all the way down to column 2 to the n. So therefore, the inner product between these two, actually, I think I want to kind of do it the other way around. And if I do it the other way around, then this matrix can actually be described in terms of the inner product between these column vectors. So this is going to be the inner product between C1 and C1, where here, again, the inner product for two complex vectors is just defined to be the complex conjugate of the first entry times the second one. Okay, so then we end up having this as our first element of the matrix. And then we would end up having the next one would be C2, C1, going all the way down to the final inner product, which would be C2 to the n, C1. The next one would, of course, be C1, C2, going all the way down, of course, to C2 to the n, C2. And you see how this pattern will continue. So if we want this to be the identity matrix, we have to argue that these inner products, Ci, Ci, is equal to 1. Or more generally, we want Ci, Cj equal delta ij, where this is the Kronecker delta function, which is, of course, 0 unless I is equal to j. So we want to be able to show this. So how do we do this? Well, the columns for each of the individual vectors are of the form Ci for the ith column is equal to it's going to be equal to E1 plus E omega. Now, if we're dealing with the ith column, then, okay, let me change my notation a bit. It's going to be a little bit easier to start with 0 as the first index rather than 1. Okay, so then we have Ci is equal to this. Then we have omega to the let's see. Oh yeah, this will be C0, C1, C2 to the n minus 1, right? And then this will be omega to the I, E1 plus E2 to the n minus 1 omega to the I 2 to the n minus 1. Okay. And all of this, of course, has to be divided by square root 2 to the n because of the square root 2 to the n. So these are the individual columns that we have from our matrix. So therefore, we end up getting that the inner product between two elements, Ci, Cj over here, is actually equal to the following. It's actually equal to the inner dot product between the two, 1 over 2 to the n, sum over, okay, well, actually, let me copy the notation in my notes, Lk. Then we have the sum over j, e to the 2 pi I j L minus k divided by 2 to the n j. All right, cool. So that's the inner product between both of them. So now what we need to do is we really just need to actually take a bit of a closer look at what the inner product precisely ends up being for this. So if we take a look at this, notice that we have this L minus K factor that we can end up writing in the following way. If we write it, oh, there's no J here. This is a scalar. So this is just the inner product between the two. And we have that this can be expressed as e to the 2 pi I L minus K divided by 2 to the n, all raised to the jth power. All right, that's cool. And this is a sum from 0 to 2 to the n minus 1. Now, this is one of the rare series that we can actually sum. This is a geometric sum. And the sum of the geometric series is actually just given by 2 to the n, 1 minus e to the 2 pi I L minus k divided by 2 to the n raised to the 2 to the nth power. Divided through by 1 minus e to the 2 pi I L minus k divided by 2 to the n. All right, fantastic. So there's a couple of cases that we need to consider. And this is the case I should mention for L not equal to K. So if we have L not equals K, then this expression is actually equal to 1 over 2 to the n, 1 minus e to the 2 pi I L minus K, divided by 1 minus e to the 2 pi I L minus K divided by 2 to the n. However, we have that L minus K is an integer, and e to the 2 pi I times an integer is always 1. Therefore, this is equal to 0 if L is not equal to K. Now, the next case, we consider L equals K. If L is equal to K, then our sum actually becomes quite simple. It becomes 1 over 2 to the n, sum from j equals 0 to 2 to the n, e to the 0 raised to the jth power, which, of course, is equal to 1. Therefore, we have that the inner product of CL and CK is equal to delta LK, and this implies that the product of our two matrices is of the form 1, 1, 0, 0, 0, 1, which is equal to identity. Therefore, unitary. Okay, fantastic. So we have that QFT, or sorry, the discrete Fourier transform is a unitary. Now, because the discrete Fourier transform is a unitary, we can actually end up considering our second property, which is QFT is the quantum implementation of Dft. Now, because quantum computers, of course, can implement any unitary, at least approximately, there exists some kind of a quantum circuit that will end up implementing the quantum Fourier transform, or sorry, the discrete Fourier transform on a quantum state. And we're going to call this the quantum Fourier transform. Now, one of the key, the matrix is exactly the same between discrete Fourier transform and the quantum Fourier transform. The main thing that's different is just what the interpretation is, right? The discrete Fourier transform, what this is this is acting on some bit vector in memory. So, this is just a series of ones and zeros. So you can envision this, if we wanted to consider like the memory layout of your computer, you might have, let's say, 256 bits here for each of the individual types. If you're dealing with something like double complex, actually, I'm not sure if it's 256 or 128, but in any case, bear with me there. So you've got all of these individual bit registers repeated for the size of the array, which is, in our case, 2 to the n. For the quantum Fourier transform, the vector that you're acting on isn't a vector of bits, it's actually just some quantum state vector in C2 to the n. So although the sizes of the operations are exactly the same, and fundamentally speaking, they're both vectors, the interpretation of the two is different. And so that's why we use a slightly different symbol, QFT, to talk about the implementation of this unitary matrix when it's assumed to be acting on a quantum state rather than a really big classical bit vector. Okay, so that's the next thing. Now, why on earth would one want to use the Dft? Well, the first is, of course, because of the fact that it approximates the continuous Fourier transform. And there's a ton of properties for the continuous Fourier transform that are super duper important. But a couple of the properties that I think are going to be really useful for us are the following. The next property is actually just kind of, so actually you can view it as just a more compact representation of the matrix definition written in Dirac notation for the quantum Fourier transform. It is of the form 1 over 2 to the n, sum over k, e to the 2 pi I jk divided by 2 to the n k over here, which of course is equal to 1 over root 2 to the n, sum over k, omega to the jk, k. If you prefer the more compact notation, it uses omegas. Okay, cool. So this here we're going to be using for the rest of our discussion is kind of our operational definition of what QFT is. The next thing is actually a really neat property. The QFT is really useful because it diagonalizes the adder circuit. So this is like, I call it like the adder property, but it really probably deserves a more noble name than that. So the adder property is if we have a unitary matrix U that ends up mapping J to J plus 1 mod 2 to the n. Okay, this is also a unitary matrix, I should note. Then what we have is we have that QFT dagger acting on U, QFT is equal to the sum over J, e to the negative 2 pi I j divided by 2 to the n of j. Okay, so what this says is that QFT diagonalizes adders. So this means that what we can do is we can use the quantum Fourier transform to take a circuit that would have added a number and make it a circuit that is kind of that multiplies a number by a phase. And similarly, we can actually do the reverse. Given a circuit, that implementation of this, the quantum Fourier transform can take that and turn it into an adder. And we'll see this when we take a look at the Draper adder later, which gives us a way of coming up with a very space-efficient version of an adder circuit for a quantum computer that doesn't have a very clean classical analog. So this is the adder property. And another property is the discrete derivative property. So this is a really important property, especially in quantum simulation, because of the fact that it allows us to approximate the derivative operation. So a discrete derivative operation can be thought of in the following way. Let's let this operator delta be written in Dirac notation as the sum over j plus 1 outer product with j minus j minus 1 j over 2h. And so what this matrix ends up looking like is it will end up looking like the following. There'll be some wraparound effects at the beginning, but let's not worry about that. What it will end up looking like is the following. It'll look like minus 1 over 2h, 0, 1 over 2h, then negative 1 over 2h, 0, 1 over 2h, so on and so forth. So you can view this as actually just the central difference approximation to the derivative. Okay, so this is an h here is kind of specifies what the step size is that you're using for the discrete derivative. Now, if we apply the quantum Fourier transform, daggered with it, acting on plus I delta QFT, then this is actually equal to 1 over h sum over k sine 2 pi k divided by 2 to the n k. So the key thing here is that QFT turns differentiation into phase multiplication. So this is another really powerful technique, and this is used in, for example, Jordan's algorithm for gradient evaluation to give you a really nice way of estimating the derivatives of a function using far fewer queries than what you would ordinarily need to do classically. In fact, it gives a quadratic advantage for the gradient, depending on how you count the cost. Okay, so that is those are all some very useful properties. Another fun fact is there's actually a connection to the Hadamar transform. Now, the reason why is the Hadamar transform actually is a single qubit quantum Fourier transform. So the way that we can end up seeing this is that QFT for n equals 1 is equal to 1 over root 2 to the 1 times 1, 1, 1 omega, which is equal to 1 over root 2, 1, 1, 1 e to the 2 pi I over 2, which of course is Hadamard. So if we're only looking at a 1 qubit space, actually the quantum Fourier transform and the Hadamard are the same concept. However, and also I should mention another trick that people often end up using, which is the fact that if we have H tensor n acting on 0, this is the exact same thing as the quantum Fourier transform acting on 0. So customarily, because a Hadamard transformation is a much simpler concept than the quantum Fourier transform, often circuits that end up looking like following: QFT, then followed by a blah, then a QFT dagger. Often this will get compiled away into this first circuit just being Hadamard tensor n, which, although it breaks the symmetry of the circuit and makes the reasoning a lot less clear, it actually is vastly simpler to execute than the quantum Fourier transform. Okay, cool. So that ends up giving us most of the properties that we would like for the quantum Fourier transform. Now, the next part that I want to kind of get at is the structure of the quantum Fourier transform and how we can exploit it in order to implement it on a quantum computer. And the main theorem, this is kind of like the TLDR of this, is that the quantum Fourier transform can be constructed using order n squared gates versus the classical version of it, which is the fast Fourier transform, requires order n 2 to the n gates. So this is an exponential speed up. However, we have the domain of the two operations is actually subtly different in this case. The domain for the quantum Fourier transform is, well, quantum states, whereas the domain for the discrete Fourier transform is actual honest-to-God bit vectors. So because of that, this exponential separation, while it looks enormous, it really has to be contextualized. For cases where we're dealing with quantum vectors, then this is an amazing speed up. However, if we really do want to carry out a Fourier transform with this, we would have to actually reconstruct the vector out on the outside. And when you consider all the costs involved in that reconstruction, actually it turns out the quantum Fourier transform is a really poor way of computing the discrete Fourier transform. But if we want to use the above properties in a quantum setting, then the quantum Fourier transform is an incredibly cheap way of dealing with this. So in order for us to do this, we need, in order to show this, we need to actually go through and make some observations. And the first observation that we need to make is that QFT can be written as a tensor product of n single qubit operations. Okay, So that is the kind of result for it, and it is actually kind of awesome for that. Well, I shouldn't say it. The quantum Fourier transform, I guess more accurately, acting on a state, can be written as a tensor product of n single qubit states is probably the best way of writing it, because the implementation of it is going to require entanglement. So in order for us to see this, let's just take a look at the action of QFT acting on a state J. Now, if we zoom back up and look at our definition, the definition of the quantum Fourier transform is this over here. So we're just going to copy that definition down. Now, doing that, we end up getting that QFT acting on J is equal to 1 over root 2 to the n, sum over k, e to the 2 pi I, jk divided by 2 to the n, k. Now, at this point, we're gonna in order to make the tensor product structure apparent, we're going to need to factor out this n-bit state over here. So let's think we can think of k as being the following vector. We can think about it as being k1, k2, all the way up to kn, where each of these is a bit. Okay, so now if we index this binary expansion that represents the value k, then we can end up expressing this as the following: 1 over root 2 to the n, sum over k1 through kn, e to the 2 pi I j k1 divided by 2 to the n, k1, e to the 2 pi I j k2 over 2 to the n, k2, times e to the 2 pi I j k n over 2 to the n, kn. Okay, and so the result follows that these are pretty much exactly the same just by combining everything up. All right, wonderful. So that is the, oh, actually, okay, let me just double check here. Right, actually, there's a little bit of a trick here that we need to do. So if we're looking at K1 going all the way up through Kn, what we need to do is we need to actually pay attention to the ordering of the particular bits. So this is actually K1 times 2 to the negative 1 times 2 to the negative 2 times 2 to the negative n. Okay, so this is our resulting bit string that we end up getting out of it. And then when we expand this out, what we end up with is we end up with the following binary expansion. Now note, using the notation that 0.k1, k2, for example, is equal to k1 over 2 plus k2 over 4, just like we would with a decimal, like a decimal. Here, we're doing the exact same idea, except now it's kind of like a binary decimal. So we're going in powers of 2 in the denominator rather than powers of 10, but it's the exact same idea. So now, once we have this binary expansion, we can end up writing this as 1 over root 2 to the n, sum over k1, e to the 2 pi I, 0.k1, k1, tensor, right, 0, oh, I'm sorry, I dropped a j in here. Going all the way up to e to the 2 pi I j kn divided by 2 to the n. Or actually, did I do this right? Let me go back here. Yeah, okay. So the, yeah, great. So then this is our expansion that we end up getting times kn. Now we can refactor this expansion just by explicitly doing the sum. By doing the sum, we end up getting, this is 0 plus e to the I 2 pi 0.jn 1 divided by root 2 tensor 0 plus e to the 2 pi I 0.j1 going all the way up to jn divided by root 2, and there should be a 1 here. Okay, so what's going on here? Why did this end up coming up in this particular form? Well, okay, first off, if we have 0.k1, then there's two possibilities. Like, let's just look at this first term. Either k1 equals 0 or k1 equals 1. If k1 is equal to 0, well, then this whole exponential ends up becoming 1, which ends up giving us this term. So we don't really need to reason so much about the k1 equals 0 case. The k1 equals 1 case requires a little bit more thought. So in that case, we have what? E to the 2 pi I. J, now I'm going to write in a kind of a weird way. I'm going to write this as 2 to the n times 0.j1 through jn. And now this is all going to be multiplied by 0.1, which is the same thing as just dividing everything by 2. Okay, which is equal to e to the 2 pi I 2 to the n minus 1 of 0.j1 through jn. Okay, and so now looking at this in a using a decimal expansion, we see that this, because this is 2 to the negative n down here, and this is 2 to the n minus 1, we can end up expressing this as e to the 2 pi I j1 through j n minus 1 times e to the 2 pi I 0.jn. Now, the reason why is that when we divide these things through, this binary fraction multiplied by 2 to the n will end up giving us, of course, j1 through n minus 1 point jn, just like we would end up getting with ordinary decimals. So I've done the exact same thing, but I factored it out. Now, the reason why this is relevant is this is an integer here. This is a half integer, potentially, depending on the value of jn. And so because this is an integer, e to the 2 pi I integer is always equal to 1. So therefore, this is always equal to e to the 2 pi I 0.jn. And so that's why this first term over here contains 0.jn and doesn't have any of the other terms, because all the rest of the terms are integers. And the same thing will end up happening with the next term over here. If we did the next term in the series, it would be of the form 0 plus e to the I 2 pi 0.jn minus 1 jn 1. Okay? And so on and so forth. So this is the form of the quantum Fourier transform acting on an arbitrary input state J. And you can end up seeing that is a tensor product of each of these individual terms. So what we'd like to be able to do is see if we can figure out a way of preparing each of these individual states on the quantum computer. Then if we can build them on a quantum computer, then the basic idea is what we're going to do is we're going to kind of begin by peeling off the bits one by one. We'll kind of like do the first bit up here. We'll get that done, and then we'll recurse on this, finishing everything up with just a single Hadamar down at the bottom. In the end, it turns out. So this is how we're going to try to do it. We're going to try to recursively build each of these individual lines from it. And so let's go through the circuit to do it. The first circuit that I'd like to be able to show you is I'll call this circuit Fn. And we'll define Fn in the following way. Let's say we've got J coming in here, okay? It is defined so that first bit, this would be like J1 coming in here, and this is like Jn down here. We apply the Hadamar transform. Then, I guess the next thing that I need to do is I need to end up defining another operation. Let's define Rk to be the following single qubit rotation. Okay. Now, you might wonder why the 1/2 to the k is coming in. This is coming in because of the fact that this will build a binary fraction that's of the form e to the I 2 pi 0.01 of this form, where there's going to be like k minus 1 zeros up here. Okay, so that's the basic idea of this Rk operation. The way the circuit is going to work is it will go through and it'll start trying to build up all these phases. Now the Hadamard creates the quantum superposition between the 0 and 1 that we need. All that we need to do now is we need to put in the appropriate phases. The controlled Rk operation will put in that appropriate phase conditioned upon the bit value J1 through Jn. So that's why we've got all of these individual controls coming in here. And the value that we're going to have is this is going to be R2, and then followed up by R3, and then so on and so forth, going all the way down to the last one, which fires up Rn. Okay, so that is the form of the algorithm that we need to do. So Fn contains these different rotations. Now let's just show that it works. So to begin with, we have that J1 through Jn under the action of the Hadamard transform maps us to 1/√2, 0, plus -1 to the J1, 1, J2 going all the way down to Jn. Okay, now I can rewrite this as actually 1/√2, 0, plus e to the 2 pi I 0.J1, 1, J2, Jn. Okay, fantastic. So the Hadamard transform automatically ends up getting the first bit of relevance that we end up needing in our phase expansion. Now we just need to get in the J2 to J3, so on and so forth. Okay, so now carrying out the controlled R2, we end up getting that this will map us to 1/√2, 0, plus e to the 2 pi I 0.J1. Now the next one from the definition of R2 will give us e to the 2 pi I 0.0 J2. And the reason why the J2 comes in is because of the fact that it will only, this phase will only be applied if J2 down here is equal to 1. Otherwise, no phase will be applied. And so this pattern of control over here for the phase is exactly matched by what we see here. And so this is 1, and we've got J2 through Jn kicking around at the end. Okay, and that of course is equal to 1 over root 2, 0 plus e to the 2 pi I, 0.j1, j2, 1. Continuing the exact same pattern for the rest of the gates over here, we end up seeing that this ends up giving us 1 over root 2, 0 plus e to the 2 pi I, 0.j1 through jn, acting on 1. Wonderful. So now then the claim is that the quantum Fourier transform circuit will take J as input over here, and it will then work as follows. First, we're going to begin with a Fn. Then we're going to, actually, let me put a second last line in here. And then we're going to apply Fn minus 1 once we've done the transformation on the first bit. That's going to fly off, and so on and so forth. We then will get F2 being applied here, finally finishing it all off with F1, where F1 is just the trusty Hadamar gate. Now, interestingly enough, you can see that trivially from this construction, the quantum Fourier transform one qubit, if we were to use this, is just F1, which coincides with the Hadamar property that we saw earlier. So it's kind of nice that that this circuit literally is a generalization of the Hadamar gate. So we have that. Following this this pattern up here, we end up seeing that this is, well, 1 over root 2, 0 plus e to the 2 pi I, 0.j1 through jn, 1. This will be 1 over root 2, 0 plus e to the 2 pi I, 0.j2 to jn. And this will be 1 over root 2, 0 plus e to the 2 pi I, 0.jn minus 1, jn. And this one, of course, last but not least, is 1 over root 2, 0 plus e to the 2 pi I, 0.jn times 1. Oh, yeah, I guess I got more space. E to the 2 pi I, 0.jn 1 is that guy. Wonderful. So that is the quantum Fourier transform acting on it. And you can see that the pattern that we ended up showing for the factorized state is exactly the same form, except ideally, this is the first qubit, and this should be the last qubit. However, what happened here is, just for convenience, we ended up actually scrambling the two. Where is it? Yeah. This circuit ended up scrambling the two. So what ended up happening with this particular circuit is the least significant bit over here got moved to the top, and the most significant got moved to the bottom. This could be, if you wanted to, swapped back up by doing a series of swap gates to move it up to the top, but it's kind of unnecessary. You can just keep track of the ordering of the quantum Fourier transform. So this is something that I just want you to remember, is that, remember, by default, almost all implementations of the quantum Fourier transform will switch the order of the bits. They'll turn little endian in computer science speak to big endian and vice versa. So what you need to do is you need to just pay attention to this. And certainly back in a former life, some of my colleagues actually ended up getting mystified for ages trying to get Shor's algorithm to work, because one of the papers that purported to give circuits for this actually forgot, when they were doing the quantum Fourier transform, about this bit reordering issue. So this is an example of something that you really just kind of have to pay attention to and think about. But this shows that we can do the quantum Fourier transform. Now, let's take a look at the number of gates that we end up needing. Each of these Fn's, this required n controlled RK gates. Okay, so if each of those, so the total number of RK gates that we end up needing here is going to be the sum from J equals 1 to N of J, which is just, of course, equal to N times N plus 1 divided by 2, which, of course, is an order N squared. So the number of controlled RK gates that we end up needing is order N squared. But this doesn't actually show us that the number of elementary gates that we need is order N squared. In order to get that, we need to actually also decompose the controlled RK gate into elementary gates. And so the simplest way of doing that is to use the following construction. And I'll leave it as an exercise to you guys to validate that this works. But the controlled RK operation can be expressed as the following. It can be expressed as RK plus 1, controlled not up here, RK plus 1 dagger. Okay. So the basic idea behind this is that if we want to get the RK gate, we can use the fact that RK plus 1 squared is equal to RK. So by using that property, we can see that if this bit, for example, was 1 and that one was 1, then we'll get the same phase as an RK gate applied to the inputs at this point. And in turn, because the C0 gate will end up flipping the 1 to a 0, the RK inverse won't end up firing. Now, if you go through the rest of the patterns for all the possible input bit strings, you'll see that in every case other than the case of 1, 1, either phases aren't going to accumulate because the bits will be 0, or the phases that get picked up will be counteracted by the phase of the inverse in right here. And so in all possible cases, we can end up seeing that the exact same phases kicked back from this is equal to that. So that's how the construction works. But the key thing that we end up needing is that there's order 1 RK gates per controlled RK. Okay, and furthermore, RK plus 1 can be implemented using 1 RZ operation, because it's equivalent to RZ up to a global phase, although controlled RZ is not equivalent to controlled RK up to a global phase. That's another fun fact that people get confused about. So we have that this is true. So our total cost estimate is that the quantum Fourier transform required order N squared controlled RK gates, which translates to order N squared gates taken from the standard set, RZ, H, C0. Okay, so that ends up showing that we can actually carry out the quantum Fourier transform in polynomial time. I should mention, though, that N squared is actually not optimal for this. We can end up getting complexity that ends up going like O tilde n, where the tilde notation means dropping non-dominant logarithmic factors. So there's like logs and potentially double logs in this, but we can get it down to an approximate version of the quantum Fourier transform that uses order n gates up to log factors. And this was due to Cleve and Watrous have an excellent paper that ends up showing a construction for doing it, but there's a number of other highly efficient constructions that get this down to linear. So this is not necessarily the most optimal, but it's the simplest. And the nice thing is that it's actually exact, unlike some of the more efficient approximate methods. So that is that. And so next lecture, we're going to be going in to applications of the quantum Fourier transform, and I'll show you how you can use this for eigenvalue estimation. Thanks a lot, and see y'all next time.